Assalamualaikum and good day everyone. Our topic today is ordinary differential equations, which also known as ODE. Okay, let's have a quick look introduction about the ODE. So ODE is actually an equation that consists of the y function fx and its ordinary derivative. What does it mean? Let's take a look into this equation. Say we have y equals to x squared plus 3x plus 2. Okay, when you see this equation, it's only have one independent variable, which is x. This one is independent variables, and also one dependent variable, which is y. This equation we call as an algebraic equation. But for other equation like this, we not only have variable x and y here, we also have its derivative variable in this function. So this is derivative variable. So this kind of equation we call as ODE, ordinary differential equation. Unlike the algebraic equation, even some of the algebraic equation is quite complicated to solve, ODE also cannot be simply solved by the traditional methods. So therefore, we need to use numerical method to do the estimation or approximations. So for the case of ODE, we have two types of solution. Firstly is to identify the initial value, or also known as IVP. It stands for initial value problem. For IVP, it's only involve first order differential function. So it means that your ODE have y prime or dy dx or function fx. These three is actually the same. It represents the first order differential function. There are several methods to solve IVP, which are Euler's, Taylor's, Hune midpoints, and fourth order Rangi-Kutta. But in this class, we only focus on the Euler methods and fourth order Rangi-Kutta. Then the second solution of ODE is to identify the boundary value, which also known as boundary value problem, BVP. For this one, your ODEs contain the second order differential variables, either in form of y double prime or d square y over dx square or f prime xy. For this type of ODE solution, we only focus or we only discuss how to solve it using the finite differential method. Now we move to the example to solve the ODE using Euler's method. So the question is solve the IVP y prime equals to x square 1 minus 3y with y0 equals to 1 at x equals to 0, 0.1 and 0.5 by using Euler's method. If the exact solution is this question, find the absolute error. First thing first, we identify what are the information given to us. Okay, so here we have the IVP function. Okay, then we have the initial condition, which are comprises of y0 is equals to 1 and our x equals to 0 with 0.1 and 0.5. So what does it mean? How we can translate this information of equation x? So it is actually the value in this column is actually represent the step size of h. So this is h, which is step size. Then these two value is actually the boundary. Okay, or we can say that the range of x value. So for the example, for these questions, the x value to consider is between 0 and 0.5. Okay, this is the boundary. X between 0 and 0.5. Then the equation of exact solution is provided as well. So this is the equation for exact solution of y. So to solve IVP using the Euler methods, we will use this formula. So the h here is referred to step size. Then we can substitute the equation of y prime from the questions into this formula. So now we have y I plus 1 equals to y I plus h is equals to 0.1, our step size, and our equation y prime I is highlighted in pink, which is x square 1 minus 3y. So we can simplify it into y I plus 0.1 x square 1 minus 3y. Okay, this is the equation that we will use to solve the IVP. Only then, now we can start our calculation. The first step is by preparing a table like this, which have 5 columns. So the first column is for the I value, the second and the third column for x and y value respectively, the fourth column for the exact value of y, and the final column is for the error value. Okay, we're starting by filling up the second column, which is the value for x. As we know from here, you know that your x boundary is between 0 and 0.5. So start your x value with 0 and add with the value of step size. So our step size is equals to here 0.1. So 0 plus 0.1, so we have 0.1 here, 0.2, 0.3, 0.4 and 0.5. So we stop until the final value of boundary 0.5. Then after that we can fill up the first column, which is start with 0 until the end. So for this question is until 5. Then the next step, from the initial value provided in the questions, x0 here is equals to 1. So put the value y0 is equals to 1.0000. So make it 4 decimal places. So I make it in the same color, so it's easier for you to refer later where the value is coming from. And now we can fill up the exact value of y on the fourth column using this equation. So for the first row, you already have the value of x is equals to 0. So our x here is 0, y0 is equals to 1. Okay, then put this value x equals to 0 into the formula that highlighted in yellow, and you will get the exact value is 1.0000 as well. And now how to calculate the error? The formula for error is the absolute value of y exact minus y for each row. So now for the first row, the error is 0. Then we proceed to the second row to calculate the y1. So to calculate the value here, we will use the data above and substitute into this equation. So now insert the equation into the calculator. Y equals to y plus 0.1 x square 1 minus 3y. Okay, then calculate. Insert the value of x0 and y0 as highlighted in the blue. So our y now is 1.00 equals, and our x is 0. So we get our y is 1. So write down your y value in the column 1.0000. So calculate your y exacts. So now your x1 is equals to 0.1. This one is referred to here, and y1 is equals to 1.000. This one is referred to here. Okay, so to calculate the y exact, just insert the value of x equals to 0.1 into the equations highlighted in yellow. So we will get 0.9993, and our error now is 0.0007. Then proceed to we will use this data to calculate the y2. So just insert using the same equation. We calculate by inserting the new y value. Y value now is 1.000, or just 1, is equals to, then our x now is 0.1. So our y2 now is 0.9980. Then calculate the y-exact, insert the value of x2, which is 0.2, into the yellow highlighted formula. You will get 0.9947 with the error 0.0003. And now you got x2 is equals to 0.2 and y2 equals to 0.9980. And use this formula, this data, to get the value on the following row. Complete until finish. And now we have the approximation data for our ordinary differential equations.